All right, so not much to say about reminder. So for your lab number 1, it has been released for quite a few days already. I gave a very detailed walkthrough about how you should really get started for lab number 1. You should really get started, but as I promised, I'm going to put down the contact information of a TA on the e-class. So I'll get it done very soon, definitely before Wednesday, let's say. So you can also reach out to the TA, but you can still make use of my office hour, 3 to 4 p.m., Monday to Thursday. If you come today, you're more than welcome to. And also, I will be attending the scheduled lab session this week, I'm pretty sure. So just come to ask questions. As we cover more and more materials for the course, you can also feel free to catch me in the scheduled lab session, ask me questions related to the slides, about the labs, everything related to the course. All right, guys, any questions so far? Okay, not much has been covered, so we'll get there. Let's do a very quick recap about what we said last time, just to remember what we covered. Very important, we talk about validation versus verification, right? So you want to make sure you really understand the distinction between them. And 3342 and 4315 are more like a sequence of formal methods course we are learning for your degree. So you want to make sure you really understand validation and verification, and also how you can do these two tasks formally. All right, precision, completeness, and also about the conditions about, for example, let's say your that your implementation should really satisfy the requirements, right? That's something we said last time. And this diagram over here is really something we spent quite a bit of time last time to build from scratch. Just remember, this will be some very practical so-called commuting diagram for you to actually implement any verification or validation using automation. You don't necessarily want to use do verification validation manually. It's not going to scale for your application. You may want to think about how can automate the process. So that might be something you want to put in your tool set once you get to the need for in your job. All right, I'll leave the practical work to you, but that's the principle. Okay. All right, and then we talk about the distinction between mission critical versus safety critical, right? You can look at the definitions also on the slides. What I want to draw more of your attention will be so-called the criticality levels, right? So that's a very standard way of defining what will be the consequence if your system fails. So in order to be safety critical, you have to make sure your system will fall into either catastrophic or severe consequence if it fails. Otherwise, anything other than that, like a major, minor, or no effects, is only at most mission critical. Cannot be categorized as safety critical. All right, just remember the criticality level. That's really the takeaway for this particular page. And we talk about how to relate these two claims about a system being mission critical and a system being safety critical, right? So the answer should be this claim over here, C2, is a much stronger claim, which means there will be fewer systems that are going to be safety critical compared with the system that will be mission critical, right? We also talk about how to relate them using a diagram over here. We're going to see this diagram maybe again when we talk about program verification. It's a very standard diagram to really show. Whenever you got the implication over here, that simply means on the left-hand side, it could be just a subset of the right-hand side over here. All right, once we get to the program verification, I'll revisit the application of such diagram again. So you guys should really know how to apply that as well. All right, that's pretty much what we covered from last Wednesday. All right, if no further question, let's now move on. Okay, so my plan today definitely is to finish off the introduction. I still owe you that example to really show a small example like a counter. How can we use model checking in this course versus theorem proving like in 3342? You want to see an example to really see exactly how these two approaches should be compared. And I'll give you a little bit more insights and notes once I get there. But before that, just a few more things. All right, so this will be this is last slide we went over last time, just about formal methods. You can look at the definition. But just remember, formal method really is about things should be done formally using mathematics. That's the most precise and complete way of doing things. All right, so verification versus validation. So this is really repeating what we said in the computing diagram. So we are not going to waste too much time, but I just want to point out something additional to you, all right, very quickly. All right, of course, you guys have already heard about building the products right. This will be verification. Building the right products will be validation, right? That's what we said last time. For that one, you can also note down yourself. This is the commuting diagram that we set last time over here, right? In order to, for example, verify over here, we should really try to translate, and then try to verify, well, try to check or prove. So this part here is really what we said last time. I just want to point out this part over here. Okay, that's also important in practice. When we talk about implementation, you don't necessarily build everything from scratch on your own. Instead, let's say you're doing your Java projects. You don't necessarily have to use the primitive array to build everything from scratch. You may have to use a Java library, for example, array list, hash map, etc. So those are some external library components that your implementation rely on. Okay, now I'll put it down here just to make the point. So the point is, for your implementation over here, this will be some extra layer that we didn't really consider in the computing diagram from last time. But let's now address that very quickly. Does not necessarily how about it's not? I think that'll be better. It's not necessarily built from scratch. Instead, library classes might be used. Library classes might be used. So I'm not too sure if you guys heard about some principle back in the first year. You don't really want to reinvent the wheel whenever you can avoid, right? Don't reinvent the wheel unless you really need to. That's kind of the principle. Whenever you can reuse some library classes in the programming language you're using, you should really reuse it, right? When you're doing your projects. You really have to. Right? So that's some principle you may have heard of. I just want to draw some quick connection. And because of this principle, we have this reliance, we have this dependency on the library components. All right? For example, this one here could be, for example, Java library, collection library, let's say. And if you talk about Python, they also got a huge library about machine learning, training the model, right? Or visualizing the data. Similar, Java collection or Python machine learning. Right? So what's really important about this is if my implementation itself has to be somehow proved formally that it conforms to the requirements. What about the component itself? Do I actually have to formally verify the library I'm using? Ideally, yes, if you have time and have the resources, but practically, no. You don't really have that resources to really verify the whole library. You don't. So practically, not feasible to verify these components formally. Instead, well, you should still really try to verify that to some extent. So rather than formalizing it as TLA plus or formalizing it as Rodin or other formal tool, what you can do instead is extensive testing. Okay. Instead, what you learn in the software engineering testing course. Instead, unit testing. So you can see, in order to really do something formal, but behind the scene, we may have to do something that's not exactly formal. But that's something you have to kind of compromise in reality, right? All right, very good. Any questions? Yeah.
When we did with TLA Plus, what we were doing, we're going from informal requirements, creating the system properties, and then checking with the system model, right?
Yeah, exactly. Yeah, that's what we're doing. I can maybe try to revisit this diagram again, maybe after your lab number 1, as we try to reflect on that. Normally, I'll try to review a little bit once the submission deadline is passed. Yeah, you can also try to see how these diagrams here specifically can be instantiated to the different problems we're trying to solve in the labs. Yeah, for sure. But to be very honest with you, I think the labs that we're going to do for this course is not that large scale. So what we are really talking about in formal requirement here could be some requirements documents, which we don't really supply in this course. But when you actually have to do it for your industrial job, you may have to consider that later. Yeah. All right. Okay, let's now move on. That's about verification, validation. We are all good. Okay, so let's go back to the slides. Yeah, you guys can go over this about these 2 slides about verification, validation, right? Everything has been set already. And this slide here, just to kind of say, if you want to catch defects or catch bugs, basically, in your software, in order to really do it in a minimum cost way, which stage should you really do it, right? So I want to, I did mention some like a life cycle for your software developments. I can also refer you to this page over here that just gives you a little bit more details. You can think about this more like a summary of what you have learned so far in your degree, right? For example, you have learned about requirements. That's in 4312, about your requirements engineering course. You learn about how to go from natural language, which itself is very confusing by its nature. Could be incomplete, can be ambiguous, can be contradicting. Because whenever you're talking to your customer, most likely they don't know what they really want. So you have to go with them and work with them and figure out exactly what they want. So requirements elicitation is really to make sure the requirements for which all the subsequent stage is going to be based on, they should be as precise as possible and as complete as possible. So requirement here is really the most important stage, to be honest, right? And then we got design, and this is what you learn, for example, 3311, right? And it's really like a blueprint, like a sketch about how, for example, if you're doing OO, how the classes should be related, and also if you're doing database, how the ER entity relationship diagram should be drawn. You know, like a design. You don't necessarily have the executable and testable code just yet. It's not necessary. Just design. Okay. And then we got implementation. Here you got, for example, 2030, 2101, or if you're used to the old term, 2011. Right? Also, you can think about 3101. In some way, it's also very beneficial for your implementation whenever you have to be creative about a new feature. Right? So just cannot be emphasized more, efficient data structure and also algorithm. Right? And also, you talk about unit testing, JUnit test cases, for example. Finally, once you have released your product, it's not the end of your life cycle. You have to keep supporting, right, the customer. So they may accept for now, but they actually may complain about some bugs, in which case you may have to release a subsequent version of your product, right? Or in the worst case, you may have to recall, which hopefully you don't want it to happen, right? Very quick sketch about the different phases over here. But intuition is, this typically will be the earliest one. You want to get the earliest one as correct as possible so they can save the cost for later. If you can only reveal some issue of your products only at the release stage, it's going to be much, much more costly than if you can release it in the requirements phase, of course, intuitively. The earlier, the better. So the conclusion is the earlier to reveal a defects or bug, the less costly it is. you try to, right? The earlier, the better, all right? Yeah, good. Yeah, of course, you can, beyond the course, you can also try to maybe use this diagram here to think about what you guys have learned already in these courses, right? So you have already completed all these courses. So once you graduate, how do you apply all the knowledge together? And you can think about for this course, we are more around over here, 3342 and 4315. We don't really write Java code or Python code, but we're just trying to work out exactly some requirements and some design and try to see if things are consistent, right? Model checking in this course. We're around this range here. Alrighty, let's now go back. Yeah, so the rest of the slide is pretty straightforward. Yeah, this will be, well, let's say that's the life cycle. And of course, in order to be minimum in terms of cost, you should really catch the defects, for example, in the design compared with implementation, right? Should be designed as early as possible to be more precise. And this is some chart. I also supplied a reference to you at the end. So according to some IBM report, so if you imagine that, if you're able to catch the defects for the defects of your software, let's say it costs 1 unit of money, could be 1,000, could be 1 million. If you're trying to catch the same defects in a later stage, let's say in the implementation, it's going to be 5 times more costly. If you're trying to catch that maybe in the integration testing stage, which is later, it's going to be 10 times. And if you're trying to only catch the bug in the release stage, wow, 30 times more costly. And this report here is a little bit dated, so now might be even the case. Right? So the point is, the earlier you can catch the defects, the better. All right. Yeah, you can go through the rest. And here is a report over here. You can also feel free to take a look if you're interested. But I already summarized what you should know. All right, so I would like to now, let me see, the plan will be, I want to go over, oh, just before that, sorry, just one more thing. But the plan, let me go over one more thing, and I'll come back here, just one more thing. And this one is also for you guys' information, right? And for those of you who might be interested about software certification, so you can see I put a keyword here called certifying, right? Certification. And there is a method called assurance cases, which we don't really cover in this course. I just want to mention the method very briefly in the introduction part for this course. For those of you who might be interested, you can definitely search for assurance cases. You will see tons of literature talking about this method. But you can take a look, but I'll just give you some intuition about how what assurance cases really mean. In order to build some assurance case, basically you're drawing a tree. And the tree is actually going to make some arguments about some claim you're trying to prove. I'm going to give you one example, but let's say if I want to make sure my bridge controller, which you learned in 3342, is actually reliable and fit for use, what kind of evidences do you need to supply? And the way you're going to structure the evidence is going to be in a tree structure. Okay. So you can look at this particular example here. That's for another example, right? I'm not going to go over that. But this will be something, assurance case, each assurance case will proceed. We got some top level claim. It's like a top-down approach. It can be more like a general tree. Doesn't need to be binary. It's a claim followed by some subclaims. And you can go as deep as you like for subclaim. And when you get down to the leaves, it will be individual evidence. Right, so that's kind of the structure. Right? And let me now give you one example right away. Okay. Let me just, okay, good. Okay, I'll give you an example here. Assurance case. Assurance case. Let's say for bridge controller, which you also get a chance to review slightly in your lab number 1, just for the initial model. But bridge can be bridge controller or whatever product you're building. We can say we start with the top level claim to say the bridge controller is fit for use. So this will be the top claim. Start with that. So this is like a claim. And then I can have two claims. Let's say subclaims. Subclaim number one, let's say it is correct and maybe safe. That's subclaim number one. Subclaim number one. And also for the subclaim number two, I can say not only that it's correct and safe, which is for sure should be the priority, it is also efficient. So this will be subclaim number two. All right, so I think that is enough claims we have seen. Let's now, what about at the leaves level, at the bottom level? Let's say for efficient, right? You may actually have some performance analysis, just to run the bridge maybe under some stress test and see how much or how much time it's going to take to really handle some busy requests, for example. I'll just put performance report. Performance report. It could be some stress test or load test. All right, so this could be one evidence, or what you guys learned back in 2011 or 2101, you can perform some asymptotic analysis on the paper, maybe for certain algorithm that you have adopted for the bridge controller, for example. Asymptotic analysis. And let me emphasize, when I say asymptotic analysis, I don't really mean to apply this to every part of your system. It's not feasible. Maybe only certain critical algorithm. For certain critical algorithm. All right, so that's about the efficient part. And let's now talk about correct part, which can also nicely kind of put the full methods course together to see what kind of evidences you can supply. Okay. So evidence number one, we can say it is correct by construction. This might kind of ring the bell because we learned about it in 3342, but I'm going to review that also very briefly. By construction. Sorry, the spelling is not very clear. I'll do it again. By construction. And for that one there, you can supply maybe some rodent proofs, for example, or sequence proof by doing some refinements. Okay, so this one here, you can say some refinements proofs. It could be something in rodent or it could be manual. You can decide. And you can also you can say it's also safe because you kind of check all safety property. And that one there, for example, we can supply some module checking report from maybe TLA Plus. All right, so finally, just notice that in order to really achieve this particular subclaim, you shouldn't really only try one single method to achieve it. Normally, you might need multiple methods covering different parts of your system. Each one of them is going to cover some subpart. That's more feasible approach. All right, so you can do one more over here. This can be some testing report. And for testing, I can name a few. You can do unit testing, you can do integration testing, and etc., right? What you learned in the software engineering test course earlier. That means in order to really show that the overall goal, your bridge controller is fit for use, we are supplying multiple evidences from different angles. Only 2 of them are actually more formal. The other ones are more or less semi-formal. Right? Doesn't need to be completely mathematical. Doesn't need to be. But having mathematical verification will be a very nice addition to your toolbox. Okay? So you can definitely choose to use it if you think that's useful. All right, as I said, this assurance case is not really formally covered in the course, but I thought it's definitely relevant for you guys. Later on, if you want to somehow justify to your supervisor or to your customer that the product you have built is actually fit for use, you can definitely refer to assurance case. It's a nice way to present your arguments. Okay. All right, any question about assurance case? Yes, Ferrets.
How would you argue that this sounds like for the next slide where you were writing?
Okay, which one?
Like you're arguing the bridge controller is fit for use because it's correct and safe and it's efficient. What if this does not sound? What if you're missing more? Like being efficient and correct and safe is enough?
That's a very good question. Okay, what Ferris was asking is basically about, logically speaking, let me emphasize that. That's something I would consider as a natural limitation for assurance case. Good question. Let me say this one here is subclaim number 1. Subclaim number 1. And this one over here is subclaim number 2. And this is the overall claim you are having, which is C. What Ferris was really asking is it really the case that SC1 and SC2, once you have satisfied these 2, are they sufficient to really show that C is satisfied? That's basically what you're asking, formally speaking, right? I would say it would be, for assurance case, this may not be the case all the time. In order to really show the structure over here, sometimes you may have to make certain assumption. You're saying that as far as I can provide evidences for, in order to show fit for use, these are the 2 I can show. But somehow this will be more like a communication process between you and the customer. Let's say you present this assurance case to the customer. Somehow they're asking, oh, if it's only these 2 you're presenting, what about this? Maybe another subclaim. Have you considered that? If you haven't, it will be an ongoing process to say, okay, maybe I can add another one and do more work to certify, right? So think about assurance case. It's not really like a logical proof you're doing. It's more just a way to present the evidences and what you have done in terms of verification, validation, in a hierarchical manner. Yeah, this one here, not necessarily all the case, all the time. Okay, this one here, not necessarily. Okay, you need to convince whoever you are presenting the assurance case to, like your customer, all right? I had the same confusion when I first saw the assurance case. I was wondering, whoa, maybe having these 2 may not be enough. Maybe what about another one? If another one turns out to be also a concern of your customer, then you got to do another one. If these 2 are pretty good for them, you don't need to, right? That's the informal part. Okay. All right, very good. Let's now move on. All right, so I would like to now compare what we learned in 3342 and also what we're going to learn in 4315. Okay, and for the 3342, let's now review that in just one single slide. That'll be enough. Okay, and I'll give you some example as well. And then we'll move on to talking about something called state space, which is also very important to understand about the model checking challenge we have for this course. And then we're going to do that example together. Okay, one thing at a time. Let's now do 3342 in the next 5 minutes. Okay, quickly. Okay, in 3342, we're doing basically modeling and formal reasoning. So formal reasoning over here is proving. We want to do sequence proof or refinement proofs. We do all these before we try to do any code. It's actually the same thing for both 3342 and 4315. We are not really trying to write code. We are basically constructing our model and prove its correctness before we ever try to write any code. The model that we have proved can be the basis for writing code later, but they are not the code itself. Okay, that's important to realize. And this, so both 3342 and 4315 will share this part, right, about modeling and formal reasoning and no coding. And what's really a model? Just as some definition, in case you're still wondering. Model is simply some abstraction, meaning that we're creating something that's simpler, just enough, simple enough, by filtering out irrelevant details. Anything that's not relevant, we don't need to include it in our model. You can think about for every additional detail you have to introduce to your model, you have to add some additional variables. And for every additional variable you want to add to your states, to your model, the resulting state space is going to be too huge for you to do formal reasoning, right? You got to always strike a balance. And this sentence here is also very important. I'll read it together with you. A system model means as much to a software engineer, you guys, as a blueprint means to an architect. Blueprint, not really code. The model is so important. In this course over here, the model we have is a Pascal model, even though it looks like code, but it's not really code, just model. All right, so this will be the essence for what we learned from 3342. We basically got a series of models over here. Okay, let's now review very quickly. Okay, so it's something called correct by construction. The idea would be you don't really want to have a single model. What's really a no-no over here is a single model containing all the details. Instead, we want to have a series of models, and we try to distribute the different variables and the different properties we want to verify into different models. In every model, we are trying to introduce different variables, and we want to prove different properties. Okay. And what we said was M0 at the leftmost over here, that's how we started with. This will be the most abstract model. And for example, all the way to the end, you can think about the n here. I'll just make it very general. N here can be 2, for example, right? Since we start with index 0, if I go all the way from M0 to M2, I got 3 models: M0, M1, and M2, etc. So n here can be any number in general. Okay, so this will be the most concrete. And arguably closest to the final implementation. Closest. Okay. And if you're trying to look at maybe 2 models in the middle or any 2 adjacent models, and this is where the refinement comes from. Okay, over here, apparently you can see that MI over here is more abstract than MJ. Symmetrically, MJ here is more concrete than MI, right? That's obvious. Okay, so we say that formally MI is refined by NJ. Okay. Intuitively, when I say refined by, that means it was added with more details. Added with more details. And the details over here typically would just mean variables. Typically. Variables or maybe some constraint, but mainly about variables. And in order to really do this refinement formally, what we learned in the entire 3342 is about the various so-called proof obligation. All right. To really show that the refinement itself is really the refinement in in the most formal sense, we got to prove some formal obligation. Proof obligation, beg your pardon. Do you guys remember, just give me some example about what kind of proof obligation should we formulate and prove? If you guys remember. There's several. De la Freedom, I like it. We're not going to go into detail, so don't worry. Just for you guys to brush up a little bit. Dialog, freedom. Give me at least a few more. Invariance, okay, good. But for invariance, we can prove two things. One is about establishment and also maintenance, right? Very good, thank you. Establishment and also preservation or maintenance. Okay?
Initializing system?
That's basically establishing the invariance. Initializing system. Life lock, I like it. Because we got dialog freedom, you also got to make sure you got life lock freedom. And just in case you guys remember, in order to somehow prove about life lock freedom, there is some special construct we have to introduce to our system. Do you remember what that construct is? Amber? Variance, thank you, very good. Okay, very good. Okay, I think that's good enough. So you just guys got to remember, in order to do correct by construction in the future, not for this course, don't worry. I'm not going to ask you details in these unless I cover that again in the lecture. So later on, if you do decide to really go by this formal approach, these are the checkpoints for you to recall. Or maybe just go back to the materials for 3342. All right, that's good enough for now. And failure is not an option. That's a famous quote. I put it here. Right? Should be true for 3342 and 4315. And I want to just give you one more example, and then we can move on to, defining one more thing, and then we'll do that example together. All right, so the same idea over here, but now we are having basically the n here being equal to 2. So we got M0, M1, and M2. Okay, I just want to point out very quickly. So for the bridge controller, if you guys kind of remember, right, if you took it more than a year ago, just try your best to recall. In the beginning, we don't really have the notion about bridge. We somehow collapse the idea about island and the bridge together as a one single compound. And then we got either island and bridge as one thing and also mainland. And then we only got two events, ML out, ML in. That's the so-called initial abstraction. Right? So that's what we got, M0. So this is the initial abstraction. And in 3342, we covered two refinements very quickly. In the first refinement here, which is M1, so M1 refines M0. The complication or the extra layer of concreteness we're adding is a bridge, one-way bridge. If you compare this diagram here and this diagram here, we do have the bridge. So this is so-called added concreteness. So this is the bridge, which is one way. So this is the added concreteness in the first refinement. And when we move on to the second refinements, we actually added two traffic lights over here and also over here. So this is the further concreteness we're adding. Further added concreteness. All right, good. Of course, we may not actually have time to really go into the details for each one of these. That's something you guys already learned before. Yeah, if there's any specific details that you will need, let's say from these kind of models from 3342 that will be necessary for your assessment, I'll let you know explicitly. So I'm mentioning this in the introduction because we just want to compare about the two courses is necessary. All right? Good. All right, let me define one more thing, and then we'll do that example together. So what I want to define is something called state space. This is very crucial concept to understand about this course over here, state space. Okay, state space over here. And there is a definition here. Let's read it together. The state space of a model is the set of all possible valuations of its declared constant and variables. Okay, so here you want to watch out for the constants and also variables. Okay, so these are the two things which are the case in 3342, and in your in this course TRA plus the Pascal, you also have you have a similar way to define constants and variables. And when I say valuations, possible, you can think about, let's say, for example, if I have, let's say, some constant C, and I say that C is a member of, let's say, the type, right? I got to give a type for this for the constant. It could be, for example, as easy as, let's say, 1, 2, and 3. As easy as that. So think about this one here is the type of the constant. And what about valuations? Valuation will be to consider how many possible values that C can actually take during the lifetime of your system. Well, in this case, obviously, it should be 3. You agree? Should be 3 possible valuations. So the number of valuations of C should be equal to just the cardinality of its type. In this case, it will be 1, 2, and 3. And if you guys recall, this is a set, and the vertical bar here is a cardinality for the set, right? In this case, it's 1, 2, and 3. So number of valuation will just be equal to 3. All right? Exactly which 3? Could be 1, or it can be 2, can be 3. We'll talk more about valuation maybe later when we talk about specific examples. The more valuations there might be for your state space, the more demanding it is to check it automatically. That's a very important insight you want to see right away. The more valuations of variables, constants, the more, let me say, computationally demanding. Demanding it is to check properties. So here, when I say computational demanding, when I go over with you the counter example, you will also see what it really means. But I'll give you a very quick preview. In order to really do model checking, given some system description, you're going to build so-called reachability graph, which is the graph I kind of show you on the screen on Thursday last week, right? That's something also you'll learn how to draw from lab number 1 automatically. So the reachability graph is the graph on which the model checking algorithm is actually going to build and also check for every state to see if every state is going to satisfy, for example, the invariant property. If there's a particular state or at least one state that does not satisfy the invariant property, the algorithm is going to tell you, no, your system is not correct. Okay, something like that. But we'll see more example later. And what kind of algorithm do you think the model checking tool is going to use in order to build a reachability graph and check something to reach as far as it can. What kind of algorithm, which you guys learned earlier? It's an algorithm that's a very fundamental for graphs. Depth first search. Okay, good. No trick, depth first search. Which you don't have to worry for this course. Okay, you don't need to implement it yourself. TLA Plus already implemented for you. Okay, computationally demanding, it is the depth first search on the graph. And I'll give you a little bit more intuition very soon. All right, let's just do one example very quickly, and then I'll give you some idea about if you want to do model checking, when your state space is so large or even infinite, it's simply not feasible for you to do model checking. What you can do instead, which you have to do in your lab, is to really constrain about the range of values for constant and variables. That's something we'll see. All right, so let me give you some example here. Okay. Let's go over these examples very quickly, and then we'll take a short break, and then I'll start with that small example. I think that'll be it for today. Okay. So let's say this, if you recall, there was a bank system tutorial that we did in 3342 in the very beginning. Okay, so let's say we in our bank system model, we have two constants. We got one variable. So the state space is going to depend on the range of values for the two constants and also the single variable. So we got two constants, C here and also L here. Okay. So C over here is the lower bound for the balance. The lower bound for the account balance. And the L over here is the upper bound. And let's say to start with, we simply say C is a member of, do you remember what M1 really means? Natural number? Positive, well, without a zero, positive natural number. How about that? So M1 is positive number. Okay, so both of them are positive. As soon as you see this without any further constraint, you realize the system itself is already infinite. Because how many possible valuations are there for C? Infinite. It can be from 1 all the way to plus infinity, right? Theoretically. And we got another thing over here, right? That's also what we learned in 3342. Okay. So do you guys remember? Oh, this symbol here, we may not review right away this week, but we might need this symbol when we talk about label transition system, when we talk about temporal logic. But just for now, do you remember what this means? Partial function. That's good. Okay. So here, if you look at just this expression alone, this will be the set of all possible partial functions between the string and the integer. All right. So this is something I'll see if the logic of if the temporal logic needs that, I might have to review. But for now, I just want to brush up quickly. So this will be the set of all possible partial functions between the string and integer. Okay. And we're saying that the accounts is just one of them. And we got some extra constraint. Right? We're using universal quantification, which I'm going to review maybe on Thursday when we start the review on the practical logic. And you also need to watch out for how you can express the universal quantification in the TLA plus. I mean the plus cal. I'll give you guys some reminder on Thursday. All right, we're just saying for every ID, and the ID should be in the domain of the account. And the domain of the account is a string. It can be Bill, can be Alan, can be Mark, right? Just the account name. And we say that for every such account, the account's balance, accounts over here, if you apply the name, it's going to give you the integer, which will be the balance, right? And we're saying the balance should be bounded by the credit level and the upper bound, basically, right? So that's basically what the math is trying to express. All right, we want to see some example quickly. All right, question number 1, which I'm going to give you answer right away. we want to see some example valuation or configuration for this initial model. Okay, let's see some configuration. It could be that, let's say, when the bank is first initialized, we have to give maybe some value for C. C could be 100, and L could be 500, right? That means everyone's balance should be between minus 100 and 500. Okay, that would be the range of legal limits for the balance. And the accounts over here, it should be like a partial function. And remember, every function is more like a relation. And the way we kind of represent relation is like a set of tuples, right? That's what we learned earlier. And you can say accounts will just be empty set. As easy as that. Just one example. Another example. Let's say we change maybe C from 100 into maybe 5,000. And the L here maybe to maybe 10,000. Right? Because it can be any positive number. And then the accounts over here, rather than being empty, what we can do is we can try to put in some owners of the account. For example, string here, I can say maybe bill maps to maybe 6,000. Just two examples. So having some example configuration for your system usually is good because it can just give you some idea about how the system is going to look like. But the next question is more serious. How large exactly is this initial model state space? Simple, infinite, right? Okay, it's going to be infinite. All right, you want to really think about, as soon as you got C, you can see C here is N1. Also, you got L is a member of N1. According to math, these two already, cardinality is infinite. Just so many, okay? And if you think about if model checking is actually going to do some depth first search on some graph, there's simply no such graph because the graph just cannot be built. We got simply so many possible states we have to be included in the graph. Just not possible. And also, you can see one more thing here I want to also show to you. You can see another variable here, accounts will be also string. Partial function, right? Integer, of course, it is infinite. Also, the string here is also infinite, right? Because string can be maybe empty string. It can be a string up to maybe length 10, in which case maybe it can give you a little bit more bounded. But just in general, string, it can be arbitrarily long. Which is a large number of valuations for the string. All right, so far what we have covered is if you actually got what you used to declare back in 3342, if you got N1, N1 over here, for example, also you got a set of all possible partial functions, and etc. Conceptually, we learned about how to understand them. They're just math. But in order to really build a graph and model check it, it's not feasible because state space is too large. What we want to learn in this course is when you are building your model in the different labs, we have to somehow put some limits on the possible valuations. I'll give you some example. To be, I say model checkable, okay? That means the model checker is able to actually go over all the states. Need to restrict the state space. For example, I'll just give you some idea. So here, rather than saying C is a positive natural number, why don't I say C is only 200? Rather than having the infinite possible values for C, I would say just one possibility, just 200. That should be enough. Meaning that if my system can shown to be working when C is actually 200, it should work when it's 199, an even smaller number or even larger number, right? And I can also say L would be, let's say, 600, all right? Let's say. And for this guy over here, rather than having a string, I can say maybe the account owner, rather than being a string, I can say let's limit that to only two owners. Let's say Bill and Steve. Only two possibilities, right? Bill and Steve. Oh, sorry about the spelling, but you see what I mean. I'll just write it more properly. All right, finally, let's say for this particular balance over here, so rather than maybe having the infinite integer, you can put some interval, right? Just some interval value. You can just put some interval. Yeah, I wouldn't give the exact interval over here, but just the idea. But we'll see that later in some lab. All right, let me recap very quickly, and then we'll take a short break. The definition for state space, guys, you want to get used to it. It's really about how many possible ways to really numerate the configuration or valuation for your system, depending on all the constants and variables you have already declared in the model. And it can very easily run into a situation where the number of possible valuations is simply too large, just infinite, in which case you just cannot build a reachability graph to model check. Okay? And just for your information, which is also mentioned somewhere in the slides, when the state space is too large, we say that we got something called state explosion. It's a term people use. State explosion problem. All right, that's something for your information. And we shall reinforce this concept over and over throughout the course. Okay, that's good. Any question so far? Good. All right. So why don't we pause here and then take a short break by taking attendance. If you can. Okay, the last bit about introduction is to really use a small example and show to you how the 3342 approach is going to be different from 4315 approach. Let's see. Okay. I think for the slides, that's what we covered before the break. And also you will see the definition for state explosion, right? That's what we learned. That's what we mentioned before the break. Okay, you can also see state explosion. And this part here, yeah, this just related to your lab. I will mention that maybe a little bit later. Okay, let's go over this example together. Okay, let's now learn about a small problem, and then we're going to see how we can apply the theorem proving rodent approach to it, and also how we can apply the model checking approach to it. Okay. So let's say we got very simple state space, an integer counter C, just that. Okay. You might be wondering, if that's already integer, wouldn't that be infinite? You might be right, but bear with me, because the way we're going to set up the constraint is going to make sure the reachability graph, which we're going to build, will be finite. Okay, we'll see that. You can, if you got that doubt, very good, but just keep that just for now. So integer counter C, that tells you this will be the state space. All right, very small. And let's say we have some safety constraint. So we got some minimum value and some maximum value. For example, C value should be between 3 and 10, let's say, for example, right? That's the only safety constraint we have. And we got two kinds of updates here. We got unconditional, which means it should always work, which is to initialize the system. If you recall, in 3342, we learned about an event called init, initialization. So let's say initialization is going to put C as 0. Straightforward. Of course, minimum value should be at least 0. Well, should not be more than 0. That's what I meant. Okay. Okay. So here, assuming that, okay, assuming that 0 is larger than or equal to the minimum. Okay, just in case you're wondering. We also got conditional updates. This will be the interesting bit. Let's say we got 2 possible updates. We can either get increments or decrements. And what we need to figure out, what you guys need to figure out as a professional engineer, in order for me to do increments, can I do increments unconditionally? Always. Obviously, I cannot. Because remember, we got a safety constraint over here. Okay? So what I want you guys to tell me is, so under what circumstances can I increment? I need some formal constraint over here. I'll start with you. Go ahead.
C is strictly less than max value.
I like it. Very, very precise. All right. So guys, you may want to do a very quick exercise just to yourself. Why cannot say C less than or equal to max? All right, because if C happen to be just max, adding 1 to it is going to go above the max. So that's not good. So it must be exactly this. All right. Symmetrically, we should only decrement when you are strictly larger than the minimum. Okay? Very important. All right. Let me leave this page clean over here. And I'm going to actually show to you both approaches and see how the time goes. Maybe I can only finish the detail for the 2 approaches, and then I will use this page here to summarize the 2 approaches as the first thing on Thursday. We'll see how that goes. But that's a problem we have. Okay, let's get to something that you kind of learned in 3342. All right. And of course, in order to make it very precise, I would need to maybe give you some rodent project to really try it out. Let's not bother. Okay, I'll just give you enough information so that you can see the idea. So there are 2 parts over here. So theorem proving. Now you want to formulate the model. Number 2, discharge. Bless you. Discharge, proof obligation. These are the 2 things, basically. Of course, you can think about as part of the second step, you also have to formulate the proof obligation first before you can prove it. Right? All right. All right, let's now take a look. Let's say for part number 1, okay, let's see what do we need. We got some constants, maybe. We got some constants, in which case, let's say we got a minimum, and also we got a maximum. Let's say we only got these 2 constants. And to really constrain the constants, we need something called axiom, right? That's also what in the rodent, you can say either it's a theorem or not a theorem, right? When you say it's not a theorem, it's an axiom. So we got axiom over here. And the axiom is pretty simple here. Let's say the minimum itself, let's say it's a natural number. Doesn't need to be positive. And also the maximum is also a natural number. And notice that we are not doing model checking, so there's no state explosion problem we have to consider. All right? Whenever you're doing proving, you just basically do mathematical proof on the paper. And let's say we got another axiom here. Why don't we say the minimum should be always less than or equal to maximum? That's about the context, right? If you remember the term. So this part over here is so-called the context, okay? So this part over here is the context. And the static part. And to really define the dynamic part, we will have variables, invariants, and events. So let's say we got variables. And there's only one variable called C. And then we have invariants. And typically there are two kinds of invariants. Number one will be more basic, just to give the type, called a typing constraint. And the way our naming convention is, presumably this is the initial model for the counter. So it will be model 0. It's possible we may want to introduce some refinement later, but let's say this will be the initial model. So the naming convention will be, I would say, invariance 0, which is for model 0, and then underscore invariant number 1. All right? That's a label. And then I can say C here is a member of natural number. So this is something more basic, so typing constraint. Typing constraint. All right, and let's have the second invariance. I can say invariant 0, still model 0, but number 2, right? The second invariance. And here I can put the safety constraint, which we talked about already. I can say the minimum less than or equal to C, conjunction, and the maximum less than, oh, sorry, beg your pardon, C less than or equal to maximum. C less than or equal to maximum. It would be your choice to say, if you don't want to put them using a conjunction together as a single invariance, you can say, I want to put this one here as a separate invariant number 3. That's fine too. Nothing wrong with it. So what we have over here, this is so-called safety constraint. Right, you got typing constraint, we got safety constraint. All right, so let me just remind you, this part over here is the dynamic part for the system, and that'll be the machine. Oops, I do want to make it dashed. All right, so this part over here is the dynamic part, which is the machine. Okay, machine dynamic. All right, like that. That's about formulating the model. So what we have done is just step number 1, formulating the model. That's the model we have. And step number 2, we can think about 2.1, is to formulate a proof obligation. And you guys just helped me brainstorm quite a few. And the one I want to do will be invariant preservation, let's say. Okay. So for step number 2, about invariant preservation, about proof obligation. Proof obligation. Oh, actually, I forgot about events. Beg your pardon. So I'll leave step number 2 here for a little bit later. I definitely mean to, you know what? Let me do the following. Machine dynamic. Okay, let me just delete this part. Sorry, I kind of missed my notes there. So we also need to have events. And I do have some important things to say over here. For events, we got increments and we got decrements. Let's say for increments, as you guys correctly said, this increment here should be conditional, which means it should not be enabled all the time. It should be disabled sometime. So it will be disabled when, it should be enabled when C is strictly less than maximum value. Let me just put this guy here, maybe right here. Okay. Okay, it's called a guard. And also you have begin. So I can say the counter value will become C plus 1. right? And just for completeness. Decrements, the guard should be, the C should be strictly larger than the minimum, and also begin. So here C becomes C minus 1. And all right, so this will be the dynamic part. And like that. All right, dynamic part. We got variables, we got invariants, we got events. And just to also remind you about this one here, that's really the guard. Or enabling condition. If this condition here is not true for the system states at the moment, then this event cannot happen. It's disabled. So this concept here is very important when we talk about how the model checking algorithm is going to build the reachability graph. It's kind of related. Right? All right, so now let me go back to step number 2, proof obligation. Okay. So for proof obligation, we are only talking about invariant preservation. So invariant preservation simply says we assume all the constraints, including the invariance, is true before each event. So thinking this way. So let's say, think about each event is more like a state transition. So if I got my state over here, I got my state over here, right? If you guys remember, we talked about pre-states and also post-states. And these two concepts will come back again when we talk about the program verification later. Let's say, for example, if we try to do increments, right? Just take that as an example, increments. So if I try to go from the pre-states of increment to the post-state for increments, I know that the change is going to be defined by the action for the events. I'm going to increment the value for C by 1. But what's more important is for invariant preservation. We are saying that here we assume invariance should be true. In the post states over here, we are trying to prove or establish the invariance. You can say still hold, or they are preserved, or remain to be true, right? There are different ways to say that. Let's say are preserved to hold. So starting from a state where it is safe, you want to make sure the post state here is also safe. Proof obligation, right? So that's for invariant preservation. And there are 2 of them. Yeah, let me just finish a few more things, and then I'll make sure I end the class in time. Let me write a few more things. And I'll give you guys something to maybe brush up a bit before Thursday. So here, there are 2 relevant proof obligations. Let's say talk about increments. We want to make sure increments can actually maintain this invariance. It can also maintain this invariance separately. Okay? So what I will write down is, for the event name will be increments. And then I want to make sure it will invariance 0, 1. And then, okay, how do we read this? I'm talking about the events increments, INC. And I'm talking about the invariance, this one here, which is here. And then I'm saying INV is about maintenance of the invariance, the nature of the proof obligation. And there should be another one. The same events, but a different invariance. Invariance 0 underscore 2, which is about this one here. This is something we will try together. Okay, invariance. This one here. Okay, I got about 30 seconds, so this is what I will do for you guys. Okay, let me just switch the page very quickly. And I think that this might be the only time where we're going to do this in detail. But as I said, it's very valuable to really compare the two courses. So you really see the value of knowing both. All right, so before Thursday, if you guys can try, but of course I'll give you the answer. You want to see if you can formulate, just formulate, don't need to prove. The proof obligation, which will be the increments in variance 0, 1, and also I and V. Okay. I know for those of you who took a 3342 just last semester, you may have some advantage. But you guys, if you want to brush up very quickly, this might be the nicest way to really brush up the course. I'll give you guys some hints. You should really formulate as a sequence over here, where you got certain hypotheses, you got a sequence, turnstile, and also a single predicate over here. That will be the format of your answer. So on Thursday, we're going to spend about maybe 15 minutes maximum. I'm going to show to you how to formulate the sequence, and we'll do some little proof together. And then we'll move on to compare how this approach, incompleteness, is compared with the model checking approach. All right, we'll start from there. All right, thank you so much. I'll see you on Thursday. Wednesday, I meant.